Okay guys, so this is learning timetable number 5. There it is. And so this is your homework for this week. And again, it's practice of 3 exam questions. I've gone all high tech. I'm in my office still, so I'm filming the next 3 in my office. I've gone all high tech today. So I've got the cheat for you, but look what I did. I cut it up into the 3 questions there, so we could leave that one on. How good is that? Okay, so let's just get rid of those and let's do this first question. This first question here, I hope you had a go at it. It's unbelievably complicated. So that's just confusing really, isn't it? Okay, and this is where, I'll just move that up there. Okay, this is where you really need a diagram for this. So here we go. I'm even going to, good practice, get a ruler in here. Okay, and draw a line. There you go, straight line. So we've got 3 posts, P, Q and R. So I'm going to go P, Q and R. It doesn't matter that it's not to scale this. Those are my 3 posts in a straight horizontal road. The distance from P to Q is 45 metres. So I'm going to put 45 metres. And the distance from Q to R is 120 metres. 120 metres, there we go. The car is moving along that road with constant acceleration, so the acceleration is the same all the way along there. Metres per second. We don't know what that is. And there's the speed of the car as it passes P is u, so we don't know what that is. U, metres per second to the -1, the initial velocity. The car passes Q 2 seconds after it passes P. So this leg of the journey takes 2 seconds, and it goes on to tell you that the car passes R 4 seconds after it passes Q. So 4 seconds there. Okay, so that leg of the journey takes 2 seconds, and obviously it's accelerated, so it's going faster. That takes 4 seconds, but it's further, and so on. So we've got to find the value of u and the value of a. So this takes a little bit of thought, how you're going to do this one, because there's obviously lots of bits that we don't know. Let's just change these glasses. They're falling off my nose because I've broken them. There's lots of bits we don't know because we don't know the velocity here and here, and we want to try and avoid using those. So the way that I'm going to avoid and do this question is it's got to have distance in it. So it's got to have, we want something with s in it because we've got lots of s, haven't we? The distance here, the displacement. But it has to have u and a in it because we've got to find those things, and it's got to have t in it. Well, u, a and t, it's going to be s equals ut plus a half at squared. Okay, so we've got that, and it's these two. There's 2 unknowns, but we can set up 2 equations here. I'm going to set up the whole thing, okay? So the whole thing is 165 metres, isn't it? That is from P to R. So the whole thing, I'm going to go s equals ut plus a half a t squared, and the whole thing is 165. Is equal to u times t. Now t is 6 seconds, isn't it? So it's going to be 6u, that's u times t, but written the right way round because it took 6 seconds to do the whole thing. The time is 6 seconds. 6 squared is 36, and a half of that is 18. So I'm going to go plus 18a. We don't know the acceleration. That's one equation. If we just look at p to q, okay, then we can go s equals ut plus a half a t squared for that. The distance from P to Q is 45, and that is equal to the time it takes to go from there is 2, so 2u, we don't know the initial velocity, plus a half at squared. Well, the time is 2, 2 squared is 4, a half of that is 2, so 2a. Okay, so we've got 2 equations, 2 unknowns, it's simultaneous equations. We could do a substitution. I'm not going to do a substitution, I'm just going to do elimination. Okay, I'm going to times this by 3, and 3 lots of 45 is 135, is equal to 6u plus 6a. and then I'm going to write that underneath here. So 135 is equal to 6u plus 6a, and I'm going to do a simple takeaway. 35 to 6 leaves me with 30 is equal to 12a. So I've got 30 divided by 12, so the acceleration is just 30 divided by 12. 6 goes into both of these, doesn't it? 6 goes into that 5 times, and 6 goes into that twice. So it's 5/2, or 2.5 meters per second squared. That's the acceleration. And then if we put that into either one of these, and I'm just going to put that into this one, this first one here. So we've got 45 is equal to 2u plus 2a. The acceleration will be 2 lots of 2.5, so it would be 5. Take 5 off both sides. 40 equals 2u, and divide by 2. U is equal to 20 meters per second to the minus 1. There we go. Wasn't too difficult, was it? The difficult part of that question, of course, was the diagram originally and thinking about which formula to use once you've done that. I'm sure you'd agree it's straightforward. Okay. Next question is that one. This one actually, there's a lot of writing, but they've done all the hard work for you because they've done a nice diagram. So let's get rid of that. Let's put that one up there. And all of this text here is just explaining this diagram. So let's just have a look what's happened. So this lady, is it her? Yes. So this lady has sprinted from start. She's accelerated with constant acceleration to reach a speed of 9 meters per second. She's kept that's taken her 4 seconds. She's taken a constant speed of 9 meters per second for the next 16 seconds. So she's 20 seconds into her race, and then she decelerates and passes the finishing line after 25 seconds. Okay, so that's and that's how she does her 200-meter race. Okay, and we've got to find the distance covered in the first 20 seconds, the value of u, and the deceleration. Straightforward. Okay, so all the information is there. So the first 20 seconds is this first part here, and this first part here, if you look at it, is that shape, and we know that the area underneath the velocity time graph is the displacement, and we know that in the distance covered in the first 20 seconds, so we want that area there. Okay, and that area, well, how do we find the area? Well, from just GCSE, it is a plus b divided by 2 times h, isn't it? Or h over 2 times a plus b for the area of a trapezium. Okay, so we've got the 2 parallel sides, so it's 16 plus 20. That's top is 16 and the whole bottom is 20. That area, let's put them on. Divided by 2 and times the height is the distance between them, which is 9. Okay, so we've got, I'm reaching for my calculator now, because I've got 16 and 20, which is 36. Divided by 2 is 18. 18 times 9, can't do it in my head, is 162. Okay, so I'll change my A for an S, displacement. So she's travelled 162 metres. The value of so this bit there, she decelerates to go through. She's tired, isn't she? Okay, she can't keep that 9 meters per second up. So she slows down a little bit to pass the line, and we want to find out what she slows down to. That end piece there is also a trapezium, isn't it? And that distance is u. Okay, the bit that she gets down to, and that distance was 9, and it's over the last 5 seconds. And we know that all of this area is 162, and it's a 200-meter race. So if you take that off 200, you get 8. It's 38, isn't it? So that area is 38. So again, if we go 9 plus u divided by 2 times the height, which is 5, distance between them, is equal to 38. So that's the area, isn't it, of that trapezium. It's like this trapezium here, but it's on its side. So those are your two parallel sides. Okay. So there we go. I'm going to times both sides by 2 to first of all. So 38 times 2, 38 times 2. It's just shocking, isn't it? I mean, it's divided by 5 is equal to 15.2. So 9 plus u is equal to 15.2, and take off 9 is equal to 6.2. So u is equal to 6.2 meters per second, and that looks feasible, doesn't it? Sensible. Okay. And the deceleration in the last bit, again, you saw me on last week's do v equals u plus at, but it's just the gradient of that line, isn't it? Of this line here, okay? And the gradient of the line is just y over x. Okay, we know it's a negative slope because it's decelerating, but the y value is between 9 and 6.2. Okay, so that's 2.8, and the x value is 5, so it's 2.8 divided by 5. 2.8 divided by 5 is 0.56. Okay, and that's a deceleration. So if you were to use that in Newton's equations of motion, you put a minus in front of it, wouldn't you, to show that it's a deceleration. It's slowing down by that per second. Okay, tea's going cold now. This one kind of made me. Alright, so that's that one. And then the last one. These are the ones that there isn't in M1 exam questions for these. So I've got these ones from the book, from the textbook, and that's because it wasn't on the old M1 papers. So again, I hope you're getting used to these now. So we're following this pattern, aren't we, of S, we integrate down and we get V, and we integrate down and we get, sorry, I'm talking rubbish. S, we differentiate down, we get V, we differentiate down, we get A. If we go back up, we have to integrate and put on constants. Okay, so let's have a look at this one. A particle P is moving along the x-axis. The velocity of P at time t seconds is this here. So it's given us the velocity, which is equal to 3t squared minus 8t plus 5. That's the velocity, okay? Just checking that's on the screen, it is. And that happens when t is 0, when t is equal to 0, p is equal to 12 meters. Okay, so it's already 12 meters down the x-axis. Find the values when p is instantaneously at rest. Okay, it's a quadratic, so it's sort of, you know, it's slowing down and coming back up or whatever. So it has has a time, okay. The values of t when p is instantaneously at rest, it's when v is equal to 0, isn't it? Okay, so this is, you know, as a quadratic, it's coming down at, this is your velocity and this is your time, so it sort of stop, you know, it instantaneously stops. This is a change of direction, so it's sort of going down, stop it, you know, slowing down, stop, and then it's coming back, and then it's coming back again. That's what's sort of happening, okay? And we're going to find those two times, and it's when velocity is 0. So when is the velocity 0? 3t squared minus 8t plus 5. I hope this is going to factorise nicely. I'm going to have a go at that. I hope it does. Oh yes, it does, yeah. 5 and 1. Okay, and this is, oh, they're both negative as well. So that's when t is equal to 5/3 and t is equal to 1. So at those two times, it is at instant. So after, you know, 1 second and 1 2/3 seconds, it's instantaneously at rest. So it's what's happening here. There's the graph. There's 12 meters. Okay, and then it's going along here, and after 1 second it's slowed down, it's stopped, and it's coming back here, and after 1 2/3 seconds it's stopped and it's going back down here, and it's carrying on that. That's what's actually happening. Okay. The acceleration of p when t is 4. So acceleration we've got to differentiate down. So dv by dt, the change of velocity in time, is the acceleration, which is equal to times by the power not 1 off the power. So 6t minus 8. So that's the acceleration. And we want the acceleration when t is 4. So when t is 4, that's part A, B. When t is equal to 4, you can see that the acceleration is equal to 6 4s are 24. Take away 8, acceleration is 16. Blimey, that's fast. Okay, that's the acceleration. And the total distance travelled by p in the 3rd second. So this is a bit more to it now. First of all, if we want the distance travelled, we need an equation with s, and to get to s, let's put this one in actually, because we worked out 6t minus 8. If we want to work to s, we've got to integrate, so we've got to integrate up. So let's do that first of all. So we've got an equation for s. If we integrate up, we go add 1 to the power t cubed, divide by the new power, so we're dividing by 3 because this is now cubed, and 3 divided by 3 is 1. Add 1 to the power, so this becomes t squared, divide by 2 now, minus 4t squared, plus 5t. So that is integrated up, but we've got a plus c on the end, haven't we? We also, it gave us some information that when t is 0, p is 12, okay? P is 12, it means it's 12 meters from the origin, so s is 12 when t is 0. And if all of that is then 0, and that's 12, then c is 12. So s is equal to plus 12, okay? So substituting t is 0 into there makes all of those bits 0, and s is 12, because that's where it's starting from. So we've got that coordinate. Okay, now this one confuses me, the total distance travelled from p in the 3rd second. So we've got to be careful with this. I'm just going to draw, so make sure I get it in my head right. Okay, so starting off at 0, t is 0. After 1 second, that would be considered the 1st second, wouldn't it? Yes, it would. That's the 2nd second between 1 and 2. And the 3rd second is between 2 and 3. So we want the distance travelled in 3 seconds, and then we take away the distance travelled in 2 seconds, and that tells us how far it travels between the 2nd and the 3rd second. Okay, so we're going to put 3 into there. So we're going to go 3 cubed minus 4 times 3 squared plus 5 times 3 plus 12, and minus, we can sort of integrate, can't we, between, you know, we're sort of integrating that between sort of 3 and 2. That's what we're doing. It's the definite integral. So we don't actually even need this 0 and 12 here. And when we put 2 into there, we're going to have 2 cubed minus 4 times 2 squared plus 5 times 2. Okay? You can do this all in one go on your calculator, and that's what I'm going to do. So I'm going to go 3 cubed minus, whoops, I'm going to regret doing this all in one go, because it's 3 cubed minus 4 times 3 squared plus 5 times 3. I'm not going to put the plus 12 on because I've got I'm going to put a plus 12, I'm taking the whole lot away and I'm going to put a plus 12 on the end of this, so I don't actually need that on, okay? Minus, but if you're unconfident with that, then you stick it on, 2 cubed minus 4 times 2 squared. Sorry, I'm painfully slow. I'm just worried about making a mistake. 5 times 2, which is easy to do with these, isn't it? And that is equal to 4. So it takes 4 meters. The noise going in the background actually is my emails coming in from all my fans. Okay, there we go. Those are those 3 questions done for the homework for this week, learning timetable number 5. Okay, and I don't think I've made any mistakes on this week. It'd be a miracle if I haven't. Okay, thank you.